Welcome to GCSE Physics, topic 5.1. We're calling this A because this is about types of radiation, and it's the first lesson on background radiation and measuring radiation. So we've got these objectives here. So objective C from the specification for this particular topic, talking about waste materials from nuclear power stations, nuclear medicine, radioaction, background radiation, random nature of decay, and artificial and natural sources of radiation. Right, so we clustered all these together because it made sense to talk about them all at the same time. Right, can you hear that noise? All right, so if you put this special type of device called a Geiger-Müller tube next to Brazil nuts, bananas, certain types of watches, toothpaste from the 1950s, lots of other things, it makes this noise. Now, a Geiger-Müller tube is a particular type of device that picks up radiation, but there are other things. For example, photographic plate. So we used to have to develop photographic film in order to get pictures, and obviously now we're capturing them on digital sensors, which are then converting those into digital images. But you can obviously use photographic plate, but a Geiger-Müller tube gives you a sort of number. It gives you an idea as to how many things are striking it. So what's the thing that's causing the noise? Well, it's radiation. And radiation is all around us, all of the time. We can't escape it. In fact, there's a place called Chernobyl, and when we look at half-life, we revisit this kind of concept. But there's actually a red, an amber, and a green zone, and the red zone is right where the red zone is right where the nuclear disaster happened, and that the radiation is pretty high. In fact, so high that they put a dome on it to try and minimize leakage should anyone get nearby, or animals and things like that. And then there's a yellow zone, which the radiation is above background, but not super high. And then there's the green zone, which is just normal as everywhere else in the world, basically. And yeah, we encounter it all of the time. It comes from space, as you can see here on this graph. We have about 1% from nuclear, and then we've got medical devices, so things like X-rays. So if you go and break your arm, you get a dose of radiation. If you go in a plane, then you would receive a dose of radiation as well, a dose of X-rays. And the rocks in the buildings, so even the thing that you're in right now, we may be giving you a dose of radiation. We've got rays coming from explosions billions of years ago, ripping their way across the universe and striking our planet. So cosmic rays. And then we've got food and drink, quite a lot of it in terms of food and drink. And then we've got this stuff called radon gas. We're going to come back to radon in a little bit, particularly if you're in Wales, which is what this course is aimed at. There is a map looking at Wales, sort of showing the levels of radiation in various different places. So exposure to this comes from a mix of background and man-made sources, and this is known as background radiation. So a Geiger-Müller tube, what you don't need to know is the sort of major inner workings of it, but you need to understand that it gets struck by ionizing radiation. That is radiation that removes electrons from atoms, molecules, compounds to make them charged in some way, or adds them, but generally changes the way that the ion moves. So ionizing, generally speaking, is about removing the radiation. And it's good for detecting alpha and beta, but not so good for gamma radiation. So you might actually get it might actually be quite a lot more damaging, but a lot of it might be missing. So because it's a gas, and gas is quite far apart, and if you watch the second course in this topic, you'll know that gamma is not particularly it's very ionizing, but it's quite penetrating as well. So it doesn't interact with material very well. And so a gas is very, very spread out and therefore not so good for gamma. And we have these atoms of inert gas and they get struck with whatever radiation, and then the Geiger molecule picks it up as a little micro electric shock. And it gives a little click, like you heard at the start of this video. So we're going to see a setup for this to help us answer this question. So this is something called Radiation Lab. If you've watched the other video already, you'll already know about it. So Radiation Lab is something you can have a search for on your favorite search engine, and it allows you to have a look at a range of different things. But this thing here is our Geiger molecule. And we can click this button on the right, which resets the timer. And you can see the event counter. So that's the number of counts per, well, it's just the number of counts. And it keeps a counter, and we can hit it again. And we see if they get the same number. Now, I'm not going to do this too many more times, don't worry. Okay, so you can see that the number isn't the same. Now, I know this is a simulation, but it's a simulation to show the real world and what the real world does. Now, decay is random, background radiation is random. We can't tell whether there's going to be a cosmic ray coming from the other side of the universe and landing and coming through the Earth from the other side or wherever. So the background radiation is a bit random. And so you can see here on the right-hand side that there is it says centimeters, and it's obviously from a particular source. So if I put a source here, it'd be 6 centimeters, and I can move it away. What this isn't doing is it's not telling me, unless I click this button, what the reading is. So this source here, this is an alpha source. It's firing radiation through the air, and it's not really changed the value very much because we're still reading the background radiation, but it tells us the distance. So if you were setting up an experiment, then you might want a ruler to say, okay, well, there's the source, and then there's a distance to the source, and then you might move it in 5 centimeter intervals and see if what the activity is like. Now I'm going to go in 20 centimeter intervals just for the speed of this video. All right, so we're going to go, well, it'll be 25, so we're going to go to 5. There you go, 6. Okay, so you could plot that on a graph, and you could say, what's the activity? You could move every few centimeters, every 5 centimeters, every 2 centimeters, to see if there is a difference. We go to 10. Does it make a difference? It does make a difference. Okay, so that if we go back to that question on you can see a lab has 3 radioactive sources that are not labeled. It's known that one of the sources emits alpha radiation, the other sources only emit beta radiation, and the third emits both beta and alpha. Explain how these apparatus can be used to collect data, and how can the data be analyzed to identify the three sources. Excuse me. So the first thing, if you haven't watched the other video yet on beta and alpha, they are types of radiation, and as you saw, alpha, the alpha source in the video, did not go very far through air. Beta travels maybe twice the distance. Um, so the first job is to measure the background radiation. So we use the Geiger-Müller tube to measure the background radiation. That's a really, really important thing to mention because we've got to subtract that number from the actual number to see it. Now we've got a 30 centimeter ruler. You saw when I doubled the distance, when I got to 10 centimeters, the alpha source basically dropped off to virtually nothing. So if that's air blocking it, then a piece of paper would do an absolutely fantastic job of reducing the count rate on the Geiger-Müller tube. So we put our source at the end of a ruler, and you are allowed to draw and rearrange these things. We would count for 30 seconds, same amount of time each time, and we would then put the source at one end of the ruler, the Geiger-Müller tube at the other end at 30 centimeters, and we would then do a count with nothing in the way. And then we would put the piece of paper in between the source, you could say at 10 centimeters. Okay, so, and if the number drops off, we know that it's going to be an alpha. It could be if the number doesn't change, then it could be a beta or a beta and alpha. And then you put it right next to it, so 5 centimeters away, and you measure again. And if the signal is way stronger, then you've got both beta and alpha. If the signal is the same, then you've only got beta. So obviously at 30 centimeters, if we get no difference from background, then it's alpha only. There's a way of analyzing the three sources. All right, but the key thing is measure the background first, which links to what we have been talking about. So the fact that waste materials, so we haven't talked about that yet. So background radiation, being able to make an allowances. We've talked about that. And we've talked a little bit about the random nature of radioactive decay. So we've obviously got to work with repeat readings, right? So we did those experiments several times to make sure that we are making an appropriate set of data. We're collecting an appropriate set of data. So we mentioned earlier about radon gas, right? So we're going to look at natural and artificial sources of background radiation to try and start understanding how dangerous is this stuff. So radon gas, particularly if you're in Wales, which I'm assuming you will be if you're studying this course, is a gas that's naturally released from radioactive decay in the Earth's crust. And there's lots of mines across Wales that have dug into the ground and have released that radon gas. And particularly with quarrying, where you've got blasting going on and things like that, it can make microfractures in the soil, in the rock, and the gas can escape. Now, if you're in the air, well, that's fine. It just gets diluted. And as we talked about before, alpha sources, so radon is an alpha source, it's not going to travel very far, and so the radiation isn't going to get to you, and therefore it's fine. But in a house, the radon gas is going to collect. It's quite heavy, so usually it collects on the first story. And if we have a look at the location map, you can see here that South Wales, in fact, so North Wales is high levels over here as well, low in sort of England. But yeah, where there were sort of mining towns and things like that, and old mines. Obviously, just natural geology as well. It's not just about mining. Um, but you know, if you're on the coast, if you're in these areas here, then you should probably get testing for radon gas. Now, one of the measures that you can do is to seal the floor. All right, so you can get a floor seal, or you can get venting fans that help again from the bottom. And you put a venting fan in here. All right, so there are two measures, and you do need to know those things. So make a note of them. What sort of safety measures? So we've got floor seals, and we've got um, venting fans to help us minimize our interaction. As long as we're not breathing it in. I mean, the trouble with alpha sources is that if you breathe it in, then it gets in your lungs. It doesn't travel very far, but it doesn't need to when it's inside your body because it's very, very, very ionizing. Causes lots and lots of damage, which is why it doesn't travel very far. So you need to, it's worth finding out if you have radon gas, you just moved into somewhere new. You should find out if you're on the bottom floor. If you're on the top floor, it's less likely that you're going to be affected if you're in a block of flats, or your house, your bedrooms are on the top floor, and you're raised up. Probably not going to be an issue, but worth checking these things out if you are in these areas. So we talked a little bit about radioactive decay. So radioactive decay, obviously our background radiation, it's a random process. A random process means that you don't know when it's going to happen, meaning that the clicks that you hear on a Geiger counter will not be regular. So a Geiger counter will measure the radiation that's all around us. This background radiation is low level and would normally take readings for at least a minute. Many readings need to be taken to measure the background to find a reasonable average. So we've done this kind of thing before. So that's really, really critical in terms of exam questions. That's the major thing that you need to be aware of is, okay, well, what's the background? And do you do it just once? No, you do it several times. You do it at least 3 times to try and get an average reading. And then obviously, if we're calculating an average, we're talking about the mean average. So we've got value 1 plus value 2 plus value 3 divided by the sum of the values, which is 3 in this case, equals the mean. Now, this won't appear on your equation sheet, so if you don't know how to calculate an average, I would suggest you write it down. So number of values divided by the number of values. And obviously, we take repeats to improve the consistency of these values. So once we've done that, we can then correct anything. So if obviously we're trying to measure a banana, for example, we would want to make sure that we measure the local background radiation just sitting on the surface, not really doing anything. And then when we move our source material into the space that is nearby. All right, so here's how we calculate it. And this is a several stage thing that we need to know. Measure the background radiation. And then we look at the average background count, measure the source in the lab. So you calculate the mean, calculate the activity of the source, and then minus the background count equals the count rate of the source. Okay, so here is an example. The teacher uses the apparatus below to demonstrate the penetrating properties of alpha, beta, and gamma radiation. After the experiment, the teacher gives students some data about the radioactive source, cobalt-60, to analyze. The data are given in the table below. The teacher tells the class that the counts due to background radiation are included in the results in the table. Give one cause of background radiation. So think about what we've talked about so far and think about anything that might be in the classroom that might lead to the background radiation. State how the results in the table should be corrected for background radiation. So here are this came from an exam paper. So radon gas, cosmic rays, rocks, food and drink, buildings, nuclear power stations, medical uses. Accept sun or the stars, that would link to the cosmic rays. Do not accept X-rays, Big Bang, or the cosmic microwave background radiation. So the radiation coming from the Big Bang is not ionizing. Neither is light. So microwave radiation does not cause cancer. It can cause heating, but it does not cause cancer because it doesn't ionize. UV, however, so natural sunlight, is cancer causing, and it's one of the reasons that we had a big scare about the ozone layer depreciating, because the ozone layer protects us from some of these cosmic rays. And when the ozone layer disappears, well, then we increase the amount of UV and all sorts of other things. But UV is the main thing that it protects us from, and it increased the rate of cancer across the whole world. But particularly in Australia, there was a massive hole forming there. But obviously, if we kept going as we were, then that hole would have got bigger and bigger and bigger. So state how the results should be corrected for background radiation. Measure the background radiation and subtract background from all readings. All right, so that's what we just talked about there. All right, so I'm just showing you that what we have looked at. So the fact that we've just talked about the random nature of decay. We've talked about some natural and artificial sources and discussed the reasons for radon level variation. And we've talked about how to make an allowance for measurements. And we have finished that one too. So thank you for listening to the presentation. Now let's try some diagnostic questions. See you on the next course.